Welcome to the public exam review for Unit 5, Chapter 5, and trigonometric functions and graphs. In this presentation, we will solve trigonometric equations algebraically using specified domains. Here we will focus on algebraically solving trigonometric equations using a specified domain. Here are some tips that we can use to solve trigonometric equations. First of all, we can isolate the part that contains the sine or cosine of an angle and bring it to the left side of the equation. If the terms on the right side of the equation equal a -1, 0, or a +1, then we can use quadrantal angles around the unit circle to determine the solution. If the terms on the right side of the equation equal ±1/2, ±√3/2, or ±√2/2, then we can use special angles around the unit circle to determine the solution. If the terms on the right side of the equation are not one of the above, then we will have to use a calculator to determine the solution. Always sketch a diagram to indicate which quadrants the angles may be found in, and always determine the measure of the reference angle, theta r. Any restrictions on the domain indicate the number of revolutions to make in either a positive or a negative direction. So let's look at some examples. In the first example, we are asked to solve 2 cosine x plus √3 is equal to 0. And the specified domain is that all values of x have to be greater than or equal to a -180 degrees, but less than or equal to 360 degrees. So let's isolate the term containing the cosine of the angle. So we have 2 cosine x is equal to a -√3. Dividing both sides by 2 leaves us with the cosine of x is equal to a -√3/2. This is something that is familiar to us from the work we did in Chapter 4. We know that the cosine of an angle is negative in quadrants 2 and 3. So to sketch a diagram to illustrate where the angle can be found, we will put the unit circle and we will have terminal arms in quadrants 2 and in quadrant 3. We know that the cosine of the angle is a -√3/2. So the sine of that angle must be a +1/2. And this related reference angle here is going to equal 30 degrees. So then in quadrant 3, the measure of our angle, the first angle for x, is going to equal 180 degrees minus the related reference angle of 30 degrees. So we have x is equal to 150 degrees. That's the measure of x on the first rotation around the unit circle. As well, if we go into quadrant 3, the cosine of the angle is still at -√3/2, but the sine this time will be a -1/2. So in quadrant 3, the measure of this angle x is going to be given by 180 plus 30 degrees, so x there is equal to 210 degrees. I indicated quadrant 3 in the last example, but that was quadrant 2. All right, so that's your first positive rotation, which gives us all the values of x that are less than or equal to 360 degrees. However, we also need to go in a negative direction around the unit circle. So if we go in the negative direction, we are back in quadrant 3 again. And another possible value for x would be a -180 plus the related reference angle of 30 degrees. So x is equal to a -150 degrees. These are 3 possible answers that will solve this trigonometric equation. So to list those solutions, we have a -150 degrees, a +150 degrees, and 210 degrees as three answers for this equation. In example 2, we are asked to solve 2 times the cosine of 4x is equal to a -1, where x is between a -pi/2 and a +pi/2 radians. So this time the answer will be expressed in radian measure. Notice that the angle for which we are taking the cosine of is 4x, so we need to adjust the domain of the original function. If we multiply throughout by 4, we will have 4 times a -pi/2 is less than or equal to 4x, which is less than or equal to 4 times pi/2. So that results in a -2 pi is less than or equal to 4x, which we will replace with theta, to be less than or equal to a +2 pi. So let's go back and isolate the part that contains the cosine of the angle. So we would have then that the cosine of 4x is equal to a -1/2. If we replace 4x with theta, we are solving the cosine of theta to equal a -1/2. And this is something that we are familiar with. Remembering that cosine is negative in quadrants 2 and 3. So if we sketch a diagram to illustrate what's happening, we can use a unit circle, and we can put the terminal arm in quadrant 2 and in quadrant 3. The cosine of the angle is a -1/2, so the sine of this angle in quadrant 2 must be a +√3/2. And the related reference angle here this time is equal to 60 degrees, which is pi/3 radians. So then the measure of this angle in quadrant 2, theta1, is going to equal pi minus pi/3. Pi is the same as 3 pi/3 minus pi/3. You get 2 pi/3. But that's the value for theta. We need to replace theta with 4x. So if 4x is equal to 2 pi/3, we can multiply both sides by 1/4, and we end up with x is equal to pi/6 radians as one solution for this equation. So that was on our first positive rotation around that unit circle. If we continue in our positive rotation into quadrant 3, the cosine is a -1/2, but the sine this time would be a -√3/2. So then we have our angle in quadrant 3 to be theta2 will equal pi plus pi/3 radians, which is equal to 4 pi/3 radians. Replacing theta with 4x, we have 4x is equal to 4 pi/3. Multiplying both sides by 1/4 results in x is equal to pi/3 radians. So that was on our first positive rotation around the circle. We also have to go on a negative rotation around the circle because the values of theta have to be greater than or equal to a -2 pi. So if we go on a negative rotation, we can be back to quadrant 2 again. I'll try to fit it in on the screen. So another value for theta would equal a -pi minus pi/3, which is your related reference angle again. So that results in a -4 pi/3. Replacing theta with 4x, we have 4x is equal to a -4 pi/3. Multiplying both sides by 1/4 to enable us to solve for x. X is going to equal a -pi/3. That's another solution for this equation. And similarly, when we go back to quadrant 3 in a negative direction, another possible value for theta would equal a negative pi plus pi over 3. So that results in a negative 2 pi over 3. So we have 4x is equal to a negative 2 pi over 3, multiplying both sides by 1/4. We have x is equal to a negative pi over 6 radians. These are 4 solutions which satisfy this equation, and it corresponds to part C in the multiple choice items. In example 3, we are asked to solve the cosine of 3 times x plus 90 degrees is equal to decimal 6.5, for negative 90 degrees is less than or equal to x, less than or equal to a positive 90 degrees. Notice that the value of the right side of this equation is not one of our special measures, negative 1, 0, 1, root 3 over 2, root 2 over 2, or a half. So in this case, we will have to use a calculator to determine the answer. Nonetheless, we need to adjust the given domain. The measure of an angle here is 3 times x plus 90. So if we add 90 to each part of our domain, we would have negative 90 plus 90 is less than or equal to x plus 90, less than or equal to 90 plus 90. So we have 0 degrees is less than or equal to x plus 90 degrees, less than or equal to 180 degrees. But then we need to multiply throughout by 3. So if we multiply throughout by 3, we're going to get 0 degrees is less than or equal to 3 times x plus 90 is less than or equal to 3 times 180 degrees is 540. So what we will do then is we will replace 3 times x plus 90 with theta. So we have theta has to be between 0 degrees and 540 degrees. What this means, if you make one full revolution around the unit circle, you've done 360 degrees. So 180 more would bring us to 540. So that's really 1.5 revolutions around the unit circle in a positive direction. So let's go back and solve the equation. We will replace 3 times x plus 90 with theta. So we have the cosine of theta is equal to decimal 6.5. And that is something that is somewhat familiar to us. This time we see that cosine is positive. And we know that cosine is positive in quadrants 1 and 4. So let's draw a diagram to illustrate what's happening. Putting the terminal arm in quadrant 1 and another terminal arm in quadrant 4. In order to determine the measure of the related reference angle on a first positive rotation in quadrant 1, the measure of theta 1 will give us the measure of the related reference angle. And it can be determined by taking the inverse cosine of decimal 6.5. When you do that on your calculator, it is very important at this stage of the game to make sure that your calculator is in degree mode, since the answer can be expressed in terms of degrees. So the inverse cosine of decimal 6.5 then gives us the measure of the first value for theta, which is equal to 49.5 degrees approximately. However, we need to replace theta with 3 times x plus 90 in order to solve for x equals 49.5. If we divide both sides by 3, we end up with x plus 90 degrees is equal to 49.5 divided by 3 is 16.5 degrees. When you subtract 90 from both sides, 16.5 minus 90, x is equal to a negative 73.5 degrees. And that's one solution for this equation. Continuing with a positive rotation around the unit circle, your related reference angle is still going to be 49.5 degrees. So when you get to quadrant 4, the second value for theta can be given by 360 degrees minus the related reference angle, 49.5. So we have the second value for theta to equal 310.5 degrees. We need to replace theta with 3 times x plus 90 is equal to 310.5. Dividing both sides by 3, we have x plus 90 is approximately equal to 103.5 degrees. Subtracting 90 from both sides of the equation, we have x is equal to 13.5 degrees. And this is another value that satisfies this equation. So that takes care of the first rotation around the unit circle. But we need to make 1.5 revolutions in a positive direction. So if we continue going on with that, I'll just change colors so that you can see. If we make 1 full rotation around the circle and then back to quadrant 1 again, we will get another value for theta. Theta 3 can equal 360 degrees plus the related reference angle of 49.5. So theta 3 is approximately equal to 409.5 degrees. Replacing theta with 3 times x plus 90 equals 409.5. We divide both sides by 3, and x plus 90 is approximately equal to 136.5 degrees. So x will equal 136.5 minus 90. X is equal to 46.5 degrees. And these are the 3 solutions that satisfy this trigonometric equation. So we can list our answers as negative 73.5 degrees, 13.5 degrees, and 46.5 degrees. Notice that all of these values for x satisfy the original domain, where the values of x have to be greater than or equal to 90 degrees, but less than or equal to a positive 90 degrees. And in the last example, we are asked to solve the sine of 2x minus pi is equal to a negative 1/2 for 0 is less than or equal to x, less than or equal to 2 pi. So this time our answer will be expressed in radian measure. Notice though that we have to make some adjustments with the domain. The angle is given by 2x minus pi. So what we need to do is multiply the specified domain by 2. So we would have 2 times 0 is less than or equal to 2x, less than or equal to 2 times 2 pi. So 0 is less than or equal to 2x, less than or equal to 4 pi. And then we need to subtract pi from each part. So we get 2x minus pi, and 0 minus pi, and 4 pi minus pi. So the restriction then will be a negative pi, so that's half of a revolution in a negative direction, is less than or equal to, and we will replace 2x minus pi with theta, less than or equal to 3 pi. So just to indicate for us a minute where that is located. If we have x to be greater than or equal to negative pi, it means that we have a negative revolution, half of a negative revolution. And then if theta got to be less than or equal to 3 pi, then what we will do there is we will make one full revolution in a positive direction and then go right over here to 3 pi. So that's what illustrates that restriction on the domain. Just to remove that, let's go back and isolate the part that contains the sine of the angle. So if we rewrite this as the sine of theta is equal to a negative 1/2, now it looks somewhat familiar to us. And we know that sine is negative in quadrants 3 and 4. So to sketch a diagram, we can put the terminal arm in quadrant 3 and another one in quadrant 4. The sine of your angle is a negative 1/2. So the cosine in quadrant 3 must be a negative √3/2. And that gives us the related reference angle. We know here that the related reference angle must equal 30 degrees, which is equal to pi/6 radians. So in quadrant 3 then, the first value of theta will be determined by pi plus pi/6, which is equal to 7 pi/6 radians. However, we need to replace theta with 2x minus pi in order to solve for x. So we have 2x minus pi equals 7 pi/6. We will add pi to both sides of the equation. So 7 pi/6 plus pi is the same as 6 pi/6. So that's equal to 13 pi/6. If we multiply both sides of the equation there by 1/2, we will get x is equal to 13 pi/12 as one solution for this equation. So that was on our first revolution around the unit circle. So if we continue on into quadrant 4, here we will get the second value for theta will equal 2 pi minus pi/6. 2 pi is the same as 12 pi/6 minus 1 pi/6 is 11 pi/6. Replacing theta with 2x minus pi will equal 11 pi/6. So now we need to add pi to both sides of the equation. So we have 11 pi/6 plus 6 pi/6, which results in 17 pi/6. Multiplying both sides by 1/2, we will get x is equal to 17 pi/12 as another solution for this equation. And we could continue going on for another to 3 pi radians, but notice that there are no angles with the terminal arm in quadrants 1 or 2. So that takes care of our answers in a positive direction. However, we also have to go in a negative direction for half of a revolution. So if we go back to quadrant 3 again, I'll just move that up a bit and try to fit it in on the one on the same screen. So if we're back to quadrant 3 again, then the third value for theta can equal a negative pi plus pi/6. So that results in a negative 5 pi/6 radians. If we replace theta with 2x minus pi equals a negative 5 pi/6. We can add pi to both sides of the equation. So you get negative 5 pi over 6 plus 6 pi over 6. So that will result in 1 pi over 6 radians. Multiplying both sides then by a half, we get x is equal to pi over 12 radians as another solution for this equation. And continuing with the negative revolution, back to quadrant 4, a fourth value for theta is just equal to a negative pi over 6. Replacing theta with 2x minus pi. We add pi to both sides of our equation to solve for x. So 2x is equal to a positive 5 pi over 6. Multiply both sides of the equation by 1/2. And we get x is equal to 5 pi over 12 as another solution. And that represents all the solutions for this trigonometric equation. So the answers then would be given by pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And that would be the answers to solve this equation. So you can solve trigonometric equations algebraically, and you can express your solutions over a specified interval. In the next presentation, we will solve trigonometric equations algebraically, but we will express our answers as a general solution, as opposed to having a specified interval. Thank you for your time and your attention.